So we have our first presenter. Um, what is Rex? Oh, Rex is a rock star. I know Rex from some time ago, and he's been a speaker feature at Black Hat, DEF and he's part of one of our members. So I'm assuming this next talk, since we took a look at it, it's going to be pretty amazing. So I'm going to leave you with Rex and Dr. Zeng. So Rex, take it away.
So you can share the screen.
Hello, everyone. Good morning. How's everybody feeling? Awesome, awesome. So my voice may be a little bit low today because I'm feeling a little bit under the weather. They call for good. Before I come, I already warned Marco and Rob. They say this audience should be okay with it. So if you don't like the talk because of that, that's who to blame. Just kidding. It's a privilege to be here. All right, awesome. So this talk is going to be pretty dense because we have given different version of this. DEFCON last year, Black Hat this year, DEFCON this year. It's a combination of 3 talks. So if you don't understand everything, totally don't feel bad. Before we start the talk, I want to do like a quick understanding of the audience background. Has anybody ever written a kernel module? Linux kernel module? Has everybody ever, I see 2 people. Has everybody done eBPF? 1 person? Okay. We'll try to be as detailed as possible when we talk about those since the audience needs some understanding. Okay, so yeah, so really quickly introduce myself. I work at Lacework. If you're not familiar with us, it's a cloud platform company. We basically build a platform that enable the customer to protect their cloud security. We satisfy pretty much most of the use cases. You can Google us online, in CNBC forums everywhere. I basically I lead the whole project on attack path analysis at Lacework. Basically, it's one of the core technology in Polygraph. We basically ingest all these different dimensions of data, and then we predict what is the highest risk of attack that could happen in the environment. So that's more on the posture side. And then I also work on building new polygraphs in runtime detection in the company.
Yeah. So I'm Junyuan, right now a senior software engineer at LinkedIn, working on Kubernetes. So before that, I was security engineer for J.com for cloud security. And even before that, I was working on mobile security.
Okay, without further ado, let's dive right in. Before we start, I want to sort of tell the story. This manifests some of the incidents that we have seen in the past. Just a simple example. So imagine, it's Thanksgiving time in your cloud environment. There's a hacker coming in using Log4j RCE, compromise your front-end machine, right? And then it launches a reverse shell back to his infrastructure. Then he discovered a privilege escalation opportunity on the machine. Right? So he quickly escalated privilege. And then he's trying to say, hey, if any user path credential to dump and crack and further move around in the environment. And quickly, as he enumerated the environment, he discovered that, hey, there's actually a SSH level movement opportunity by reading the SSH environmental variable, right? And then he did that, he moved to the second machine using this SSH hijacking technique. So as he is quickly celebrating, right, about his progress, he find out that his access is completely blocked. He tried all these exploits again, nothing works. Now let's look at the other side of the story. Sorry, I think there's a typo. This is the defender's view, not the attacker. Apologize. So if we look at from the defender side, your cloud security team just deploy a cutting edge security monitoring tool. And the security monitoring tool allows you to monitor all the process behaviors and system call on the system. And therefore, every single steps that the attacker performed here are actually translated to like Slack alerts or dump into the system, something like that. So this is really powerful detecting technology. Let's look at a really simple example on how we can detect this using monitoring technology with system calls. Let's look at this particular example. Let's say I want to detect a program reading at channel. Okay? So I will write a rule, and the rule will be like this. I detect there's a system call and it's open or open at, and it has read permission while the system call is being invoked. And then the file name is pointing to @C shadow. And the program is not in the allow list because you have your regular program that can read @C shadow, right? Now, if the attacker is able to, let's say, modify the file name attribute, it's able to fake the file name attribute and the monitoring software returns something else, then you pretty much completely bypass the detection. So this is what this talk is about. We're going to first talk about exactly how the system call tracing works, and then we'll talk about vulnerability, and we'll talk about different type of exploitations that can happen, and finally we'll talk about mitigation and takeaways.
Yeah, thank you, Rex. So, as Rex mentioned, Syscall tracing is very important to detect any threats. This is a diagram showing how system tracing work. So basically, the Syscall calls tracing including two components. One is the hooks for Syscall interception. Another one is for tracing progress. So when the application issues a system call into a kernel, so the Syscall code path is executed. And if we attach the tracing program to the hooks, so the tracing program will be triggered to collect the Syscall information and send those information to the monitor agent to detect any threats. So the tracing program can be implemented in the kernel space as shown on the left diagram, or implemented as a user space program as part of the monitor agent. This is shown on the right side. So as I mentioned, the program used to collect any Syscall data, like Syscall arguments, is called tracing programs. This tracing program can be attached to different hooks like tracepoint, kpro, or ptrace. We'll talk about this mechanism later in the talk. So we can use the Linux native mechanism like ftrace, perf events to as your tracing program, or you can implement a tracing program totally by yourself as a kernel module, eBPF Pro, or user space programs. So the first kind of hooks is called tracepoint. So basically, it's a kernel static hook. For Syscall interception, the kernel provides two trace points, like sysenter trace point and sysexit trace point. So if we attach the tracing program to this trace point, the function called trace sysenter and trace sysexit will trigger the tracing program. So we will use the same arguments like rex and ID. The first parameters rex is actually store the Syscall arguments, and the second parameters ID actually is the Syscall number. The trace point have a low overhead for system for interception, but it only provides static interception. So in this case, we can also use the dynamic hook like kpro. Using kpro, we can register the tracing program or almost any instructions for the Syscall tracing. So when the instruction gets executed, the tracing program will be triggered. So Kpro is a dynamic approach. It provides more capabilities, but compared to the trace point, it's kind of slow. And also, we need to know how the data is stored in the stack and register in order to get the system of information like arguments and so on. So ptrace is a system call in the Linux. You can use the ptrace to intercept the system call in user space. It's a static hook, same to the trace point. You don't need to implement any kernel module or eBPF programs, only the user space program as is needed. Compared to the previous two approach, ptrace is very slow. And but for optimization, you can combine with the Syscall as a Syscall filtering to reduce the overhead. So there are also other types of the system call interception mechanism like LTP load. This approach is very efficient, but it's also very easy to bypass. For instance, you trigger a system call through the assembly code. So many of you probably heard about the cloud workload protection products. This product usually provides advanced threat detection based on Syscall tracing. So actually, there's different types of cloud workloads like virtual machines and containers that are running on the customer major VM and service containers and also the others like AWS, Lambdas. One thing I need to mention is for the service containers, it usually allocate and maintained by the cloud provider. So it usually have no access to the host. So this table summarizes how we can use the system for tracing to protect the cloud workloads. So for virtual machines, usually we have full access to the host. So we can use any kinds of the host like tracepoint, Kpro, ptrace, and you can implement the tracing program in the kernel and also in user space. You can use different tools to trace the system call like Fargo eBPF, kernel module, and also Fargo PTIC. We'll talk about these tools later. And for the VM on the custom machine, you can have the same options as the virtual machine, as long as we get enough capabilities like sysadmin or sysBPF. So for service containers, as we mentioned, you have no access to the host. So the kernel instrumentation is not possible. So we can only use the ptrace as hooking point and implement the tracing programs in the user space. The tools we can use is only limited to the Fargo PTIC. So Fargo is an open source project and is originally created by Syscall. It's a CMCF project and right now it's very popular. So in the kernel, it supports kernel module and eBPF programs based on the tracepoint. And in user space, the PTIC is developed based on ptrace. So Fargo PTIC is dedicated for the Syscall tracing for the service workloads. So we did not evaluate other security monitoring tools, but we believe the popularity of Fargo actually represent an implementation that is widely accepted by the community. But unfortunately, this kind of implementation suffered the total issue. So let's take a connect system call, for example. The second argument for this system call is called the user V address, which is the user pointer pointing to the user buffer in user space. So it's actually the socket address. So during time of check, the tracing program trying to dereference this user pointer to get the socket address. At the same time, during time of use, the kernel may dereference the same user buffer to get the socket address. But between time of check and time of use, the attacker can actually change the user buffer to make the time of check and time of use different. So that will cause a total issue. So let's take the connect system call, for example. This hopefully can help you understand how the total issue exists in system tracing. So when the application issues a connect system call in the kernel code has to be executed, and the kernel will first check if any tracing program attached to the static hook as system call enter, like ptrace and sysenter trace point. And if it is true, as you mentioned, the attack tracing program will be triggered. So after that, the kernel will look at the Syscall table and jump to the connect system call, trying to create a connection on a socket. Before the kernel return to the user space, the kernel will again check if any tracing program attached to the 6-exit hook, like ptrace and 6-exit point. Similar as the sysenter, if any tracing program is attached to the point, they will get executed. So as we mentioned earlier, the second argument for the connect system call is user pointer. So this pointer will pass through the connect system call code path and assign to different local variables, which is highlighted in red. Then the kernel will make a copy by calling function move address to kernel to copy the user buffer to the kernel buffer. And the kernel buffer is called address, which is highlighted in green. Then the kernel will call the internal function sysconnect file to create a connection in the socket. And this is time of use by the kernel to use the socket address to create the connection. Before the memory copy function, so the kernel buffer is not created. So the user pointer is the only place to access the socket address from user space. In this case, if you attach the tracing program to the static hook, like ptrace or sysenter trace point, or even we use the ptrace to the payload to attach the tracing program to any instructions before the memory copy function, the tracing program have to use the user pointer to reference the user buffer. So again, as mentioned, the user buffer is vulnerable to be changed by the attacker in user space. And after the memory copy function, the kernel buffer is created. But unfortunately, the total issue may still exist. For example, if we attach a tracing program to the 6-exit trace point or the ptrace at physical exit, the tracing program may still reference the user pointer to get the socket address. So Fargo PDIC use the ptrace for both the system call enter and exit, but it only use the setup to filtering the system call, because this mechanism is only available for system call enter. And Fargo version older than 0.31.1, the kernel module and eBPF implementation are based on 6-exit trace point. So hopefully you get some idea about the total issue for Syscall tracing and in source code level. So I will hand over to Rex to talk about the vulnerabilities and how to exploit.
Okay, so first thing is, whenever we think about this kind of issue, we look at, is this a general issue? So basically this problem exists across Linux kernels since the trace point first introduced. So all Linux kernel has the same characteristic, I would say, for both trace point and ptrace. When we first reported this bug to Falco, there was discussion about whether this is an issue in kernel or is it an issue in the security software. So we talked to the actual kernel developer on these features, and they say, no, this is not our problem, because this is originally designed for performance and debugging, and this threat is not being considered. So then the responsibility shift to the security software actually need to monitor these system calls in a secure way. the recommendation is always monitor the kernel memory instead of the user space memory. It sounds very simple, but quickly you will see how complex this is. So before I dive into further technical details, just want to go through sort of the disclosure story very quickly. And it's very fun. When we first disclosed this was April in 2021. And we have our first version of the exploit, which we'll talk about really quickly. That can compromise any sort of system call, basically. The faculty team has been pretty good. The response, very quickly, they fixed the issue. What's interesting about this initial response is because of a specific exploitation primitive we use, it's called user for FD system call. And that system call is blocked by Docker second profile by default. So if you have Docker second profile by default, and you're only running containers, then you're immune to that particular type of exploit. And so they fix in a way that they say, okay, we're going to detect the usage of user for FD system call. And if we see that, then it's indicating some kind of exploit attempts. Notice that it's a detection, not a communication, which we'll see what happens next. This is also 2021. We also evaluated Tracy from another very popular open source monitoring solution. Same issue, except the disclosure process is a little bit interesting. They basically say, oh, we know the issue, and therefore there's no issue. I've certainly seen that in the past, but anyway. So fast forward to December 2021. After we published our first, exploit, we, give a talk at DEF-CON, and we think about, hey, can we actually improve this exploit such that it doesn't use user privacy? It seems pretty impossible at the time, but we'll show you how it is possible. And then we report the new exploit. Now, I will have to actually fix the issue in a way that we'll talk about fix, but it's a more proper fix. To basically do a double check on sysenter and also sysaccess. In terms of how pervasive the problem is, we basically look at all the algo rules, and most of them are vulnerable to most of our version of it. Okay, let's finally talk about how to exploit this particular issue. I hope the issue is very clear to everybody. It's not very difficult to understand. Basically, I'm running this system call, and then the kernel is going to fetch the user space memory, and then the tracing software is going to fetch again, but that user space memory can be changed between these two fetches, right? The issue is not hard to understand. The exploit is good. Now, let's think about exploitation requirement. First of all, we don't want additional privilege or capabilities, right? Because if you can acquire that, you may just defeat the whole monitoring software itself, right? If you're a root, you can do many things. I have like thousands of tricks you can do to defeat this. We're assuming like minimal privilege. The attacker just go in through RCE with minimal privilege user and still be able to bypass everything. We want to be able to control the time to inject the delay somehow. The delay also has to be enough such that we can override that pointer. And that pointer also needs to be able to propagate to the entire system, because we're talking about multi-core systems, we're talking about multiple threads asynchronously writing to the same memory, right? Lastly, we want this to be 100% reliable. We don't want this to be a one-off, let's say I run this 50% of the time, 60, no. For bypass exploit, it has to be 100% reliable. I could run it without a damage, but we'll have to run it always without detection, being detected. Okay, so these are high-level requirements, right? Let's think about strategy number one. So here's what we want to do. We want to trigger this, let's pick a particular system call, and then we trigger with a malicious argument. And then the kernel will read this malicious argument and then perform a malicious action. And then we'll override the data structure. And then the sysax, we're basically talking about sysax retracement. And this tracing program will read the data structure, the reference by the pointer, and we already changed that, right? So it's going to read the wrong way. Okay, but there are different challenges here. How do we know when the kernel thread read the argument? Right? This can be done very easily. How can we synchronize this override with the kernel thread read? And have to force a big enough using window. Let's talk about it one more. First primitive we have to use in the first exploit is user for the system call. This is a legit system call, by the way. Like it's used by KVM, I believe, a bunch of other hypervisor technologies. The reason that this exists is, let me talk about what it does. So whenever you have a page fault in the memory, typically will trigger like kernel execution. Right? But what this system call does is you can register a user thread to say, hey, when you have a kernel page, when you have a memory page fault, kernel, please transfer control back to user space. The user space will handle all the memory management. Yeah. This is very, very useful, by the way. This is for distributed system, right? When you have distributed system, your memory is managed by this in a distributed way. So you want your user space program to manage memory globally, right? So you handle back to the memory. The management software in the user space is going to manage across the distributed system. The next sort of exploit primitive we'll use is interrupt and scheduling. Interrupt, we're talking about processor level interrupt. It notifies a processor when an event requires immediate attention. And whenever you have an interrupt, the CPU typically, will transfer control to the interrupt handler. What's very interesting is interrupt can be triggered indirectly from system calls. And there's a specific type of interrupt called cross-core interrupt, which is going to be very important here. You can trigger this kind of cross-core interrupt by typically two ways. One is hardware interrupt. So typically when you have a computer, there's some packet coming in, there's typically one CPU and that's responsible for handling that interrupt. It's typically how Intel CPU is designed, at least. Right? And that CPU will get interrupted. And any connect system call on any CPU will trigger that kind of interrupt. Next thing is process interrupt using memory management system calls like mprotect. Right, so every CPU will have translation local site buffers that cache the memory pages and the permissions. Now, if one CPU say, hey, I want to flip with memory page permission, then all the CPU need to get notified. That's how you trigger the cross-core interrupt. Next, let's talk about scheduling. So these are user space APIs, sketch, set scheduler, any user space program will call this. Of course, if you want to do a real-time scheduling, you need some additional capability. The last one is sketch set affinity. This is also very common if you want to bring a specific thread to a specific CPU. Okay, so you guys ready for the actual exploit? Let's first look at, this is very complicated to understand, so let me go really slowly. Let's first look at this side. Let's first look at our goal. Our goal is to open up malicious file using OpenNet. So first, this file name is going to point to a page that is not allocated. Okay, and our goal is to say, later we're going to write it with some malicious content. Kernel will read it, and then we're going to override it, and then trace software read it. It doesn't detect because we override it with something that will fake it, that will bypass the thing, right? Now, to set that up, we need the orchestra to do that. We need three different threads. We need a main thread. The main thread is going to pin itself to some CPU. Let's say CPU 3, and let's say, yeah. And then it's going to mmap this page, there's no allocation, there's a mmap. It's going to register user for FD thread. So user for FD thread is the second one in the middle. It can be on any CPU, doesn't matter. And then we're also going to spawn an override thread, going to pin to a different CPU because later this override thread guy is going to trigger inter-process interrupt the main thread. So they can be on the same CPU. But the CPU number can be different. And this override thread is just waiting for some conditional attack. Okay, now with this setup, we're ready to trigger the attack. We say, hey, let's run the openet with some file name pointing to page. Okay, so kernel will trigger page fault because it's not allocated. What happened when the page fault happened? You say, okay, go back to the user space thread. Please handle the page fault. So user space thread will say, oh, let me write it with the malicious file name. Take this malicious file name. Release the conditional mutex. Now the override thread will start writing the line very quickly, right? At the same time, this override thread and the user for FD thread are racing against each other. But the user for FD will be much faster. We will release the conditional mutex, return the execution back to the kernel thread. Right? And also, even the override thread override this content. It's not going to immediately propagate on the CPU. So not every CPU will see it. Right? So now you see on the left side, the kernel will do this copy for user. It's going to copy the malicious name, start doing the actual job of the system call. And the override thread will do a memory consistency update. These is CPU level fix. Basically, we use CL flush the data from the cache to all the memories. This will take some time. While this is taking time, we're going to trigger this IPI interrupt. So CPU 2 is going to interrupt CPU 3, which increases the reason window. And then this window is big enough such that the memory consistent update will show up when the tracing program reads the array, and therefore bypass the monitor. See a few nods, some confusing faces. We'll skip this particular one. We have too many things to cover here. But yeah, let's revisit. Let's think about strategy number one. I mean, when we first discovered this, we talked to many kernel people. They were like super surprised. This is impossible. But when we discover exploit strategy number two, we start thinking about, what is the sort of assumption that we're using the exploit strategy number one. First of all, we're relying on the fact that we're able to inject a delay. It's big enough for the attack to succeed 100% of the time, but it's also relatively small. You understand what that means. And you also rely on user quality. That's why, somebody say, oh, I'm going to have a detection in things, right? How can we not use this system call? Because SecCom can bypass it. Somebody can argue, oh, I don't have container workload and my Docker SecCom profile block all this. Now here's the big question. What if we can inject a delay that is order of magnitude larger than the system call execution time? Order of magnitude. Like, we don't need all these synchronization tricks. It's order of magnitude longer. So we just override it, trigger the delay, it will show up. We don't need memory consistency update. We don't need synchronization between kernel user states, right? Question is how to do this. Interestingly, if you really understand computer, you will discover that many of the system calls that are performing critical functionality are actually blocking system calls. Blocking in the sense that, there are two types of blocking, right? One is the standard blocking where system calls say, I am going to read a file. What happened then? You wait for the file system to respond. I'm going to do some networking. What happened then? You wait for a networking stack to respond. Any sort of very meaningful, even DRAM, like memory management, right? But typically memory management is more stable. So that's one category of blocking. The second category of blocking is SecCom. SecCom, what that means is when, like Junyuan earlier mentioned, when you first come into the system call, you're going to hit trace, you're going to hit SecCom. Now, seccomp is a bunch of rules that programmer program. There's no limit on how many rules. I mean, yes, there's a physical limit that sets in the kernel, but it's really large. You can program many, many rules. But computing through these rules takes time. What if you insert many, many rules, then it's going to increase the delay, right? And we'll see how that is useful. Okay, so promise this exploit. It's very hard to come up with, but very easy to understand compared to the previous one. Everybody who goes through a computer networking class in college must have, know the SIMAC act, right, between a client and server. But if you add in the system call context here, right, you have a client, let's say your client is running the security software. And then you also have a server. Let me give one additional context here. Many times when attacker compromise your machine, they will do a few things, right? They'll try to persist, to lateral movement, but one important thing they try to do is talk to their command and control server, which is controlled by the attacker, right? So let's imagine attacker compromise the client and the attacker control the server as well. So attackers say, hey, I want to connect to my command and control server. I'm going to send a connect system call, right? There's no way around it. I have to send a connect system call. There's a SIM packet sent it from a client server. Server respond with SIMAC, client respond with ACK, right? And then right after the ACK is being sent, system call will return. It will hit the return table. Trace move, and also P trace. I think that's like everybody goes through computer networking class probably understand this. Now let's add some ingredient here, right? And see how to bypass this. Same setup, except on the client, now we have two threads, right? And first we're going to call the connect system call. We're going to point the argument to the malicious IP, which is our command and control server. We also spin this override thread, right? Now what happened? The server drops the packet. It just wait, right? The client will just wait because this distributed system, this is the hierarchical established in TCP/IP. So you wait. In typical Linux system, round 2 CentOS, they will reset. And based on TCP congestion protocol, they will try a pseudo exponential delay for every retry. Okay. So you'll find after 3 retry, the next retry will come in like at minutes time range. System call is at hundreds to thousands of microseconds. And we're talking about minutes once you hit 3 retry. That's a really, really long delay compared to system call. So the override thread can just comfortably say, hey, let me override this. I don't need to do anything else. And when this server finally come back with the SIMAC, everything's already changed, right? And the tracing software happily reads our modification. You have the demo. Yeah. Let's show a really quick video demo to prove what we're going to do. Okay. So I think what we're looking at first here is the client machine. Actually, sorry, was that server machine? Yeah, server. Let's back up. That's 176. Okay, I think that's server machine. Sorry, it's been a while. Oh, yes, that's right. So then we're going to run the server side, we run an XTP program. If you're into like low-level networking programming, like more than Linux in the cloud, you're able to run XTP program. It allows the user space. well, it enable you to directly manipulate every single bit in the packet. What this program is going to do is, hey, if I see a same packet come in, then I'm going to drop the first two, not three actually. Because during our experiment, we dropped two, it will work. And then we're going to run a listening server on the server side, right? And here we're going to run the monitoring software. And it's monitoring the connections in the call. And we're also going to open Wireshark, so we see exactly what's happening in the wire, and compare the difference. Okay, so this is the actual attack program. That does exactly what we talked about in the slide. It's going to talk to the server, but also have all these bypass hidden. Okay, so very simple trust server. Now it's connected to the server. You can type some string. Server should be able to respond. Yeah. So we see connection is alive. Now you can do any sort of malicious communication, whatever you like. Okay, so here's the most interesting part. This is the security monitoring software, right? Here we use Syscall as an example. Look at what it reports. It says, oh, there's a connect system call. It's coming from this 183, which is our client IP, to 1.1.1.1, which is not our server IP at all, right? We just set it to arbitrary. And you can transfer port too, by the way. Now, if you look at the Wireshark, you see there's no communication to 1.1.1. There's only communication between 183 and 176. Right? So that shows a successful bypass. Okay, go back to the slide. Yeah, so we just talked about networking, and next we're talking about file system. You can leverage the same principle to bypass every single file system as a bonus point, you can actually bypass other system call that relies on file system. So for example, if you're executing binaries, exact B system call, what does it do? First, it's going to fetch the actual file from the file system. So it's going to wait as well, right? Okay, now I'll hand over to Junyuan and talk about this one.
Yeah, so I want to introduce how to bypass the open system call based on views. So views actually is called a user space file system framework. And it usually includes some components like kernel module, user space library, and also mount utilities. So in cloud environment, views is often used like remote storage views. With such views, you can mount the cloud objects as the local file system and also access those objects as local files. It also provides other benefits as a user space file system, like support faster involvement or development. And also usually do not panic the kernel since it's a user space file system. So this views file system is widely used in the cloud. Here's the next example showing like the major cloud providers like Google, Amazon, and like Azure have their own views. So this is an overall architecture for how showing how the views work. So when the application wants to open the remote file, so basically what it does is the same as open the local file. It will issue an open edge or open system call into a kernel. And since the file is stored remotely, the open system call will be redirect to the kernel, from the kernel to the user space. And finally, it will send a request to the remote server, like AWS, S3, or GC storage. And after a while, when the response is back to the client, the response will send back to the application through the original path. So one thing very important is the delay between the client and server is very long compared to the system call itself. So basically, we can leverage the long delay to bypass the open system call. So this architecture and showing how it works. So we have the malicious client monitored by the tracing program. It has the system call threat that is trying to open the remote file or malicious file. As we mentioned, it will issue an open system call into the kernel with the arguments, which is the pointer pointing to the user space. It will store the malicious file name. So because the file is stored remotely, the open system call request will be routed from the kernel to user space and then to the remote server. And before the response back from the server, the override threat can jump in and try to override the user buffer, change the malicious file name to the benign file name. As we mentioned earlier, the delay is much longer between the client and server than the open system call itself. So the CPU have enough time to propagate change to the other buffer and also the register and so on. So once the response is back from the server and before the kernel return to the user space, the hooking point, as you mentioned, 6-axis trace point. If we have as any like tracing program attached to the this tracing point, the tracing program will be triggered to read the Syscall argument. But unfortunately, at this point, the user buffer has been changed to the benign file, which means our bypassing succeed. So let's take a look. Let's demo it. So we deploy the backup in the GKE cluster. And we check the pods. We have 3 pods running, and we can log into one of the pods. And we check the process running inside the container. So we have a Firewall agent running. And also we have the GCS views running. The client will mount the MNT file to the remote storage in the cloud. So we check the log for the Firewall. So we only have one event generated because it just logged into the container. And we check the folder. So it's empty, which means the remote storage in the Google Cloud is empty. And then we trying to create a file called malicious file in MNT folder. Yeah, and then you check, yeah, it's created locally and also actually it's remotely in Google Cloud. Then we check the log for the Firewall. So yeah, we have one event detected by the Firewall. We're trying to open a malicious file. Then we try to do the exploit and we remove the malicious file. And the file will be removed from Google Cloud storage. And we run attack. We check the file. So it's the malicious file is created in the remote storage. And at the same, yeah, we also double check if this event is detected. So if there's no new event generated, which means our bypass succeeds.
Okay, I know we have come like a lot of content to you guys. This is the last one. We'll be quick. So we have seen different way to bypass the exit part, right? The exit. Now we're gonna switch what happened to enter. So I enter, first you hit the trees, then you hit Syscall, then you hit trees point, then the system call is doing the actual work. What we have found is that for trees point as a center, we don't know a reliable way to do the export because we didn't find any significant top to window between trees center and the system. But between P trees and the system call, there's Syscall. So can we actually use Syscall to do something to bypass P tree? Anyone familiar with Syscall? Use Syscall? Okay. Okay, same two person. So it's a kernel level mechanism to restrict system calls. It's very useful. A lot of these sandboxes use Syscall. The Chrome use sandboxes Syscall as well. What it does is, as an application developer, you can actually insert a root yourself into the application, and it can be removed later, unless the the attacker gets kernel level privilege, has some really smart tricks to remove that. So it basically allows and blocks certain system calls. These rules can be pretty complex, and it's evaluated in the first inserted rule are evaluated last. This is very important to keep in mind. So the attack is actually pretty simple. What you do is basically, before you call the actual system call you want to bypass, you insert a whole bunch of Syscall rules. And then, you're going to call the system call when the P trees, before the P trees monitors, right? We're going to have the override thread override that. I see I only have 1 minute, so I'm going to just quickly jump over this, but happy to talk more in detail offline about this. It's a simpler attack than the previous two also. Because I do want to talk about, I think we don't have much time to make mitigations either. Let me summarize it this way. If you want to do system call tracing, there's really 3 major ways of doing it. P trees, trees point, K-probe. Right? We show that we can bypass P trees is enter, P trees is exit. Trees points is exit. Trees points is enter is unpredictable. So I wouldn't say it's successful bypass. Okay? And K-probe. How do you mitigate this? One mitigation come up from Fargo team is they will compare those trees points. This is enter, this is exit. You can do the same for P trees. Of course, somebody may come up with another bypass to say I changed both, right? But nothing known today. If you want to use K-probe, the problem gets quickly very complicated because yes, you can directly monitor kernel memory, which is good, but because the Linux kernel has a variety of support for stable kernel interfaces. So if you want to support a wide range of Linux kernel, you have to go